We're going to finish off today 2.5, and once that's done, I'm going to be looking into a next section 2.6, which is limits at infinity. So we're almost, once we do 2.6 at least, we're almost finished. As far as the intro to the tangent line problem. It's been a long journey, but we're eventually actually going to get to the end and return to the tangent line problem and use limits to solve it. But before we get there, let's do some other questions. This is the first thing we're going to do. There's a number of questions towards the end of section 2.5 homework, and they ask you to essentially find the domain or the interval, because it's the same thing, where a function is continuous. So here are my 3 examples. Really, this is not new work. This is stuff that you might have seen in Math 141. All right, let's look at rational function. Rational functions have problems when the bottom is 0. Agreed? That's where the problems happen. And a function's not going to be continuous if you end up getting a 0 in the bottom when you try and use it. So all I'm going to do here is to factor this, just to make it a little bit clearer. Right, and would you agree here that when you've got a thing like this factored, it's much easier to find the places that are going to cause trouble? In fact, there's 2 of them. Isn't 8 going to cause trouble? And isn't -1 going to cause trouble? So if I ask you what's the domain of this function, which will be the same thing as when is it continuous, the answer will be any number you like, but you can't use either of these. And in interval notation, that becomes -∞ to -1, then -1 to 8, and then finally 8 to infinity. Are we comfortable with that question? Right. Find the bad guys on the bottom, and then just don't use them. In this case, don't use -1 and 8. So I guess I'll call that question A. Right, the second question is similar to a homework question.
I have a question.
Yes.
All right, so in A, for the final answer in interval notation, what about the digits between -1 and 8?
They're usable. So they're in the answer. That's them there. You see? I don't know if I've answered your question. Have I answered your question, Mike?
Yes, thank you.
Okay. Right. This guy here, you need to do a little bit of work on it because, I mean, I could put it into Desmos and show you it, but we're trying to do this through algebra. I mean, I could have done the same with this. See, if I'd put this function in, wouldn't there have been 2 vertical asymptotes and you would have seen them and you'd say, okay, there's the 2 bad places. But let's do it through algebra. Hopefully you know that the log function only exists when the expression inside is greater than 0. If you draw a normal log function, it looks like that. Doesn't it only exist for values 0 and beyond? Now, knowing that, what I now can do is say that you can only use it when that's true. So far, so good. So I need to find out what values of, in this case, v, is 1 take away v squared positive. Well, I could do 1 plus v, 1 minus v greater than 0. Or I could just do a little sketch of what that might look like. And if you do this fella, you get a -1 here, you get a 1 here, and it looks something like this. Can you see that it's only positive between these 2 numbers? Would you agree between -1 and 1? So my answer, What is the domain of this function, which is going to be the same as when is it continuous? And the answer is going to be between -1 and 1. You okay with that one? Okay, last one, I'll call it C. There's a homework question, like something like that guy as well. Here is a very messy function. And we're going to find out what its domain is, which will be the same thing as when is it's continuous. Now I'm going to tackle this in two ways, two parts. There's better ways in it. Isn't the cube root of anything totally okay? Can't I use any value I like and I'll be able to get the cube root of it? Right? If the answer inside is -8, cube root of -8 is -2. If the inside is 1,000, cube root of 1,000 is 10. So that guy, I'm just going to ignore because it has no effect on the usable values of u. Because all values can be used, it doesn't put any restrictions on it. On the other hand, what about square roots? You can't use every number in a square root because you can't get square root of -2 because that's not a real number, right? And you can't get square root of -100 because it's not a real number. In fact, for square roots, isn't everything inside the square root have to be greater than or equal to 0, I should say. Which means that this has to be greater than or equal to 2, which means that u has to be greater than or equal to half. And that's going to be 1/2 to infinity. Now, why is there a square bracket on this, but there was a curved bracket on this one? Why am I allowing you to equal 1/2? That's what square bracket says, you can use it, and not in this one.
Because you can use the half to get a square root of 0.
Not sure what you mean. You might be right. I'm just not sure what you mean, Maggie.
Well, if you plug in the 1/2, you get
right, good, yeah. So if you plug in 1/2, you can get an answer. If you plug in 1 here, you'll end up with a log of 0, you can't. So in this case, you can't use it. In this case, you can. And that is the end of that particular group of questions on continuity and domain.
I have a question.
Yes.
So on the one above, when you drew that solid line, is it true that it's the entire, you can color in that whole half circle looking thing, all numbers inside there?
Yeah, but with a little hole at the sides, because you can't use those two.
And then above, all the way to the curve, it should be solid, all the points inside that whole domain?
From here to here?
Yes.
Yes.
She means up the y-axis.
Oh,
Yeah,
the
I do.
y-axis. We don't care what the y-axis is. So there's no advantage to shading it. When we talk about domain or when something is continuous, we're only interested in what the x's are doing or the horizontal axis is doing. The y-axis, yes, does go all the way up there, but the only effect that would be to tell you what the range of the function is. And we're not interested in the range right now, so I guess we'll not bother about it. But it would be able to take all the values from here to here, yes, but it's not important for this question.
And then the bracket on the one below that, on the left, that bracket means it's a range, and on the right, the parentheses, it's a point on the one below.
I'm trying to find.
You
Here-
know how it goes bracket,
bracket.
1/2, comma, infinity
This here,
parentheses?
this is a range of values. So this means
Yeah.
that you can be any number from -1/2 to eternity, including a half.
But
Right?
it's
So this
not
is
the range, is it?
no, this is the domain.
It's a domain. Okay, because usually when you have two brackets, I consider it a range. And when here you only have one bracket and one parenthesis. So it's like
Yeah,
a range
but
on one side and a domain on the other.
No, no. This notation, you're using the word range in the way that we use it in English, like a range of numbers. But the word range in 141 is very specific. The word range just means the values in y, the vertical values that a function takes. And domain is the horizontal values that a function can be used for. So this is a, let's use the word interval then. This interval is the domain. And this interval is the domain. The fact that this has got a square bracket and a curved bracket, because that's what I call them, you call them, I can't remember, one of them's a bracket and one of them's a parenthesis in the American world, right? But I just call them square brackets and round brackets. So it's just a different word. This is a half to infinity. You can use a half, but not infinity. This is all the numbers from -1 to 1, but you can't use -1 and you can't use 1. So curved means you can't use that value. Square bracket means you can use that value. But the word range should really be used when you talk about the range of answers, right? The range of y values.
Okay.
Okay. But now we're on to our last thing. Here it is here. Give you a few moments to digest it all. It's called the intermediate value theorem. It looks a little bit messier than it truly is, but we'll talk about it in a few moments. Okay, let's have a look at this guy. What does the intermediate value theorem says? Well, it says if you have a continuous function from A to B, so you start at A and you finish at B. You know, a continuous function is basically a solid road, isn't it? You can drive from here to here and not get killed, right? Continuous function basically means it's right one single piece of string, whatever way you want to imagine it, right? So if you have a continuous function in the interval A to B, then for every value of L, so any number you like L between here and here, there will exist at least one number, little c, that has the property that f of c equals L. So can you imagine what that's saying? Is look, you're saying if you get a continuous function and it starts here and it finishes up here, right? Because it's continuous, can't you pick any number between here and here? And whatever number you pick, won't there be a guy between A and B who has that function value? In a way, it's kind of so obvious it's not really that big a deal. It's called the intermediate value theorem. It essentially says a continuous function takes all values between its start and its finish. So imagine I had a function, f of x, and I told you that it was continuous from x equals 1 to 3, right? And I went and told you that the value of f of 1 was 10 and the value of f of 3 was 20. Then according to the intermediate value theorem, there is at least one number c in the interval that has the property that f of c equals 12. Would you agree? If you're a continuous function and you start at the value 10 and then you go to the value 20, shouldn't there be some place where the y coordinate is 12? At least one. That's basically what the intermediate value is saying. Now, we can use this property to prove that there is a solution to an equation in a given interval. So, show you the one they've got. This is question 20. We're going to use the intermediate value theorem to prove that there's a solution to this fella in the interval, 0 to 1. Well, that's fine. It's actually, you could say 0 to 1 that way, it wouldn't make any difference. So I'm going to nip over and show you what it looks like in the homework and see if we can make some sense of the way they ask. Right. So use the intermediate volume to show you there's a root. That's another way for a solution to this equation. Here's the equation, and here's the interval of x's. There's no particular reason why they did curved brackets and not square. It has no effect on the property. Now, what you need to generate is a function f of x to use the intermediate value theorem on. Well, right now there isn't a function there, isn't it? Two things equal to each other. So what you do is you take it and you move everything to one side and you get that. So what you're trying to prove here is that if this is true, then isn't another way of saying it that that's true. So how do we go about proving that this function here, this f of x that we're using here, that this function actually has a solution? Well, first thing is, just to keep the lawyers happy, would you agree that this function is continuous because there's nothing that special about it, which it is? Would you agree that it's continuous in the interval 0 to 1? Yeah, it's continuous everywhere, but 0 to 1 for sure. So what we now do is we kind of pick an A and a B, and the A is going to be at the start, so f of 0. And if I plug f of 0 in here, I get e to the 0, take away 3 plus 2 nothings, 1 take away 3, I get the answer. Oops, go away. That is annoying. Can you move it a bit? I'm going to have to shrink this up. There we go. So I can have enough room to stick in -2. So I know at the beginning it's -2. Now I find f of 1. I'm going to go here and figure out what f of 1 is. I've lost my function. Here we go. There, that's where it goes. Now I'm going to find f of 1. F of 1 is e to the 1, take away 3, add 2. And what would that be? That would be e take away 1. I think I need to use symbols here. Let me check. I do. There we go. Drag, variables, sets, relations, symbols, functions. No, okay.
It's E. It's in functions.
It is in functions. Thank you
Yeah.
for telling me that. Where did I just miss it by scanning through it? Oh God,
3
there it is.
down on the right.
Yeah, gotcha. So it's basically e to the 1, I suppose. Bit clunky, but I'll do it. So if you plug in 1, what do you get? You get e to the 1, take away 3, add 2. So it's e to the 1, take away 1. Okay. Now, since f of 0 is less than 0, and f of 1 is bigger, what does that mean? It means that the function goes from a negative number to a positive number. If you go from a negative number to a positive number, isn't it guaranteed that you're going to pass through 0? You're going to get 0. And we have essentially solved that puzzle. Doesn't look like we've solved it, I know, but that's just a clunky way that this fella does it. So that's how you're going to tackle that one. That's how you're going to tackle that one. So let me show you what I would consider maybe a little bit more obvious way of saying that same thing. Right. So I want to prove that that exists. I would start off the same way that they did by creating that function. I would find f of 0 and I'd find f of 1. And f of 0 comes out fine, it ends up being -2. And f of 1 ends up being e to the 1. Oh, add 1. I made a mistake there. And then I would draw a little picture. At 0, isn't the function -2? And at 1, isn't this function, well, e to the 1 is roughly 2 and a bit and 1, so it's very roughly it's about here. Would you agree that if this function starts here and finishes here, doesn't it have to pass through 0? Right, so we're talking y value. Starts at -2, finishes away up here, which is about 3 and a bit. Because it's a continuous function, doesn't it have to cross the x-axis? So that means there is at least one number, c, such that f of c equals 0. So doesn't that mean that there's at least one place where f of x is 0? Doesn't look like you're doing much, but to me it helps to see pictures. So the intermediate value theorem says a continuous function takes all values from its smallest to its biggest, right? There's no gaps in it. It has to take every single value. Now, I'll give an example how that could be used, at least to do this in Britain. If you're on a motorway in Britain, on bridges, you know, the overpass bridges that you get from time to time, they have cameras. And there's, you know, those cameras that they take your license plate so they know who you are. You know, you get it when you do go over the bridge, right? It's those cameras. But they're also timed cameras, they're speed cameras. And they're connected to a main computer. And what they do is, at this point here, they record when you pass the camera. And then at this point here, they find out how long it took you to get to that one. Now, because cars drive at a continuous speed, and you know the distance and you know the time, can't you find the average speed from here to here? And if your average speed is higher than the speed limit of the road, you must have, at least at one point in time, have broken the speed limit. Now, you might have said, well, I could be passing this point. Let's pretend this road has a 70-mile-an-hour speed limit. If you did speed cameras at this point, couldn't you pass this one at 60 miles an hour, zoom up to 100 miles an hour, slow down really a lot, and pass this one at 60? So if you were only using radar cameras, it would look like you were never breaking the speed limit, because at the 2 snapshots, you were doing 60. But you see, this sneaky way of doing it says that your average speed was 80. even although you might have been 60 mile an hour here and 60 mile an hour here, because it's continuous, right? You can't get from 60 to 80 without passing through all the numbers in between. Then you have to break the speed limit. And what do they do? Because it's a computer and it knows your license plate, and the car is licensed to you, and they send you a speeding ticket and you have to pay it. So if you ever go touring in Scotland, and especially motorways, because they tend to do it in motorways because it's practical to do this process, don't speed. Well, actually, you're probably okay, because the insurance, the people you rented your vehicle from will get the speeding ticket. But then they will probably send you a speeding ticket bill, so maybe you shouldn't do it. That's how it works. So they're essentially using the intermediate value theorem. Right. Don't know if that helps, but don't speed. Dangerous thing to do.
Doing this process is just like a way of making sure that there is a value at 0. Is that?
Yes, that's
okay.
all it's doing. It's just saying, can you guarantee that this thing has a value of 0? Now, it's the answer is 0, not the x is 0, right? So is it guaranteed that it's a value of 0? The story I just did there was, if the average is 80, I can guarantee that you had to be doing more than 70 at some point, right? Because you started at 60 and the average is 80, you had to do 70 something. Actually, more than 70 as well. Okay, we are now going to look at our next section. I'm going to start with notes. And it's a long section. I'm just trying to get the right number. Bear with me. 2.5. So this is going to be 2.6. Limits at infinity. Okay. So there are going to be 2 versions of this. Basically, we're talking about limits that are infinite. So the first version we've already seen, but we're going to do them as well. Vertical asymptotes. And then we're going to do horizontal asymptotes. And then we're going to do the limits as x tends to infinity of a function. Now, I'm not sure how much I'll get through this, but that's what we're going to eventually be covering. Well, so let's look at the first kind, vertical asymptotes, typically VA for short. This is really not new. There is your classic vertical asymptote at x equals 3. Do you remember doing those guys in 141? Right, rational functions tend to be the ones that generate these fellas. So if I asked you to find the limit, the overall limit as x tends to 3 of this function, the answer would be positive infinity. And we all happy with that? That as you get closer to 3, doesn't the y value become infinitely large? Great. Now there are 4 types of vertical asymptotes. So that makes your life easy because there's only 4 things that can happen, right? And we're going to look at each of the 4 situations and what the limits would look like. So that was just a basic, that's what it looks like. But let's start from the beginning again, and I'll show you the first kind, which is just that guy again. And I have my own names for that. Anybody who got me for 141 might even remember what name I give to that vertical asymptote shape. Can you remember what I called it? Not many of you got me. Same when they go like this?
You called it a volcano before.
I did. They're called, that's what I call them. Now that's not mathematical, it just helps me. If I say there's a vertical asymptote and it's a volcano shape, are you all kind of visualizing what kind of look it is? It's that look. That makes sense. So it's just a word to make it easier for us to all do it without me having to draw pictures all the time. So that is a vertical asymptote. There are 3 limits that you might be asked to find in all vertical asymptote questions. So here are the 3 answers. We've already done the first one, the overall limit. You could also be asked a right limit and then a left limit. Would you agree in this case, everybody is a plus infinity? Would you give a left limit, right? You're coming in from the left-hand side, it zooms off to plus infinity. Would you give a right limit? Plus infinity as well. So that's the first situation. This one I call a hole in the ground. Just my own made up name. But if you ever hear me saying this vertical asymptote is a hole in the ground, can you see that I'm talking about this kind of shape? That's just what it means. So what do we get from this one? Well, we also get to answer an overall limit. We get to do a right limit. And we also get to, sometimes we're asked to find a left limit. Okay. No particular order. What is the right limit on this fella?
Negative infinity.
What about the left limit?
Negative infinity.
So what's the overall limit? It's not meant to be a trick question.
Negative infinity.
Negative infinity. Can you see in those 2 circumstances, doesn't an overall limit exist? Because the left limit is equal to the right limit. Now, when I mean exist, I mean that at least it is a value that we all agree on. You could argue infinity is not a number, which I agree it's not a number. But for the purpose of answering questions, can you agree that you would be putting infinities of one type or another in these questions? Because vertical asymptotes generate infinities, right? That's their thing. I said there's 4. So that means there's 2 more.
For the one you did with the volcano shape,
Yeah.
as the left branch tends to 3, would it be it goes to like positive infinity, not negative infinity? Is that just an equal sign?
These are equal signs. Oh,
On the last one, yeah.
yeah, they're all equals.
Okay, good.
And they're
Just
all
wanna make sure.
positive. So just my writing wasn't clean.
Okay, perfect. Thank you.
Okay, so you're happy now because that's what you thought it should have said. Gotcha. And there is no significance to x equals 3. You know, I'm just picking that because I felt like it, right? There's no significance at 2 or 22, it's the same results. Okay, I said that there are 2 more to go, so let's see if I can draw them. They're very similar looking, but they have slightly different results. In these 2 situations, probably not one of my better names, I call these one of each. Does it kind of give you an idea of what it is if I say, okay, this is a vertical asymptote and it's one of each? I'm talking about one of these kind of pictures, right? Maybe I should write a textbook one day. Could you imagine how scary it would be? It would be full of things like, as long as you do it to both sides rule, that's a volcano there, but the other one is a one of each.
You could call it Calculus for Dummies.
I think that title has been misused. How about Calculus for Real Dummies? Okay, yeah. I'm a great believer that things should have names that give you an idea of what the heck they're about. Even if the names are silly, I think it's still, to me, I don't know why that wouldn't be a real name. Why you shouldn't call a vertical asymptote a volcano. I mean, it's a very useful, I think, a very useful way of doing it. Okay, so what we're going to look at are left, right, and overall, left, right, and overall, and we'll see what we get here. So this bit I have to just spend all my time writing the darn thing down. And then once we've got that, we'll talk about what the answers to each of them are. I'm trying to be consistent, so I'm writing them in the same order. That's that one, and this one here then. Okay, let's start with the top guy. This one here, right? What's the left limit? So what happens as you come in from the left-hand side? What's the left limit for this?
Positive infinity.
I agreed. Would you agree the right limit is negative infinity then? What is the answer to the overall limit in this situation then?
Does not exist.
And that's the kind of answers, the DNE that you use. I think, doesn't web assign just take DNE? You don't have to write the whole sentence. Okay. So in this second situation, it's very similar to that, but aren't things kind of switch places? So if I was looking at the left limit, it's negative infinity. If I was looking at the right limit, it's plus infinity, and the overall limit does not exist. So if someone asked me to find what the limits were like at a vertical asymptote, if you gave me a picture like this, would you agree it'd be very, very easy to do it? Because aren't the answers always plus infinity, minus infinity, or does not exist? I mean, it's not like you have an awful lot of math to do, right? And if you've got it in front of you as a picture, you can certainly do it very, very easily, right? If that was the picture, you could write the answer, right? So let's pretend for a minute that we didn't have Desmos. So try to avoid Desmos in those questions where they want you to do it numerically. So I just want to show you how you could test what kind of vertical asymptote is happening numerically, right? And I want to do 2 examples of it. No, I don't have time. I want to do 1 example of it, and then I'll do another tomorrow. So I'm going to pick that guy. Now, would you agree that there is definitely a vertical asymptote at x equals 1? I don't need Desmos to know that. You agree? X equal 1 is going to cause the trouble. So we are going to do a table of values. And that table of values is going to help us to find out what the left, the right, and the overall limits would be. Now, since the problem is happening at x equals 1, your table of values should be really close to 1. And then maybe moving out a little bit, and then maybe moving out a little bit more, and then out a little bit, and out a little bit more. So I guess I don't need that one, right? So from this table, I'll find the value of this function. And what that is going to tell me is what kind of vertical asymptote it is. And if I work at it, I should be able to figure out what the left and what the right are. Right? You know, is it plus infinity or it's minus infinity? That's all I need to know. So let's go and see what happens. I'm going to type this guy in. So it's going to be x divided by a bracket 1 take away x, close the brackets, squared. I'm going to go to second table setup. It looks like it's good to go. I'm going to go second table. Oh, shit in space. Okay. I just wanted those other numbers out my way because they're kind of distracting me. Right. Okay, so 0.9, then 0.99, 0.999. Oh, shit, space. This guy here is 999,000. 0.99. My table's just been a pain in the butt. It's 9,990, and 0.9 was 90. Okay, let's look at those numbers. As you're coming in from the left side, do you see that the value is getting big and bigger and bigger? But isn't it getting bigger and bigger positive? So can you imagine that if you kept getting closer to 1, wouldn't that side go infinite on you? Positive infinity. Great. Now, if I do the other values, and it looks like in this case, I'm going to have to do them one at a time because my blinking table's not being my friend. That's 110. That's 10100. And this one is 1e to the 6. Can I tell you 1e to the 6 is just a million? Now, as you home in this direction, as you get closer to 1, aren't the answers getting bigger and bigger, right? They're getting infinite. But more importantly, aren't they getting positive infinities? So do you see in this case, that guy has a plus infinity as the left and the right. And once I know what the left and right are, can't I then decide what the overall is? So in this case, what would the overall be? Agreed, infinity. I saw your lips, Smith. We got it. Now, pretend that it was a different question, but this happened. Wouldn't this answer now be negative infinity? Right? Negative 90, then negative 9,000, negative 909. So what that would do is this answer would be negative infinity. Wouldn't this one, we'll keep these numbers the same, wouldn't this one still be plus infinity? But then, wouldn't this then now become a does not exist? Now, that means really, doesn't it, that if the expression was a really weird and ugly one that was hard to see what's going on, couldn't you simply just do a quick table of values and find out left and right infinities, left and right limits, and whether they're plus or minus infinities, and get it that way? And we do have enough time, I believe. So we're doing the original version of that. Now, the original version of that said that at x equals 1, wasn't it plus infinity in both cases, right? That was the one I did at the start. So I'm going to plug that into Desmos, and I want to see this picture, right? I want to see a volcano. If you can hold off for a few moments while I try and figure out where the heck I am. While I'm doing that, why don't you just say hi? So while I'm getting set up, you lot say hi. Okay, I'm ready. Hopefully I can share the screen. Please tell me you're watching Desmos.
Yes, we are watching Desmos.
Oh God, do you know the number of times this doesn't work when I do it? It's scary. Right, so it's going to be y equals, and my little guy here, and where's my fraction? Oh, I don't need it for this. Okay, so you go x, you hit the division button and it makes it a fraction. That's what goes on there. So 1, take away x, close the little guy, and I'll hit the square button, and then I'll make this go away. And I might even zoom in a little bit. Is there a volcano at 1?
Yes.
Table of values, verified what the graph says. That's us. Bye-bye.
Thank you.
You're welcome.